Welcome everyone to the AGN seminar today. Our speaker is Astrid, who will talk about can we bound the interleaving distance between n-parameter persistence modules in polynomial time. Spoiler alert, yes. So floor is yours.
Okay, thank you. Thank you for being here. I cannot see your faces, but I know everyone is here. So yeah, I'm gonna talk about this question, if we are able to bound interleaving distance in polynomial time, and maybe it's catchy or not. It's a yes, that's a positive answer to the question. This is my research in my thesis. I'm a PhD student in Michigan State University, and I'm working with Elizabeth Munch. So this is a collaborative work for sure. Okay, so let's start with some motivation. I can go like this. Let's see. Oh, if I click and move, perfect. So we have different topological structures that we use to characterize or to figure out the characteristics of a space. So let's see. For example, we can have these level sets that can, let me move my camera a little. They can represent a level cloud system. Sorry, and I can make this level set into a merge tree. I can take this second one, turning it into a merge tree. I have two different merge trees. I can compare them using interleaving distance, and then that's gonna tell me something about the cloud system itself. So having interleaving distance is a nice way to have a way to differentiate between two different structures. We can have proteins, and we can use mapper graphs in order to know more about them. So we can create this graph, we can n simplex, I guess, and we can have connect component cycles, and we can figure out things about. And actually, this image comes from this research from Erin Chambers, Elizabeth Munch, Sarah Percival, and Bei Wang, because they were interested in bounding the interleaving distance between mapper graphs. And they have the idea to use a loss function to bound it. So actually, the framework that we are using in this research comes from this one, but we generalize it to more general sets, if we can be redundant. So we have that framework of using a loss function to bound interleaving distance. And the final one that is really important is the multi-parameter models. So we can have a bacteria, and we can do our usual filtration, like take some balls, take the radius epsilon and start to growing. And so we have a filtration, but sometimes that's not enough in order to find the topological characteristics. And we use another thing. In this particular example, they use curvature. I think they were using the tangent plane, and they were able to do a second filtration using the curvature. You know what I mean. So now, instead of having only a filtration, we have a bifiltration, right? We have like two parameters. Now it's a multi-parameter persistence model. The thing is, when we try to compute interleaving distance with these structures, it's hard. Actually, NP hard. So I think this was proved by Professor Havar, Magnus, and Michael. Yeah, let's say first names, even though I don't know them personally. Oh, maybe Havar, I know them. But anyhow. And then we have a problem. If it's NP hard, we cannot compute it as nice. So our idea, and one of the main reasons we started this project, was, can we use this framework that was developed before for mapper graph using a loss function to bound interleaving distance into multi-parameter models? And as the talk says, the answer is yes, we can. And I'm just gonna show exactly how we did it. So let me go to the next slide. So on our talk, we're gonna have 3 points. The first one is we solve a more general problem, bounding interleaving distance between generalized persistence models. So any poset to any category. To be fair, we're using concrete categories, which means like the objects in these categories have sets as their underlying part. And we use a loss function, that framework that I was talking before. Then we're gonna optimize this computation to that function, to that loss epsilon, loss of epsilon, when the poset is exactly a product of linear orders. So let's think R2, R3, and 2, and 3, and so on. And the final thing, we're gonna show conditions to compute this loss in polynomial time when the category it's either has objects with underlying finite sets or a vector spaces with maps of finite rank. So these 3 parts, doing the loss function and optimizing for multi-parameter and vector spaces, let's say, and that will be the whole bulk. And just that you know, you can interrupt me anytime, or Bastian can interrupt me anytime if someone has any question. Okay, let's see. So let's start with our definition. This is a really categorical work, so let's go with the categorical definition of interleaving. So remember, we're using generalized persistence. Oh, I think this is a C, persistence models. So then can go from any poset to any category. And we're gonna talk about an epsilon interleaving of f and g. That's a pair of natural transformations. One is phi that goes from f to the chief by epsilon of g, and c that goes from g to the epsilon, the chief by epsilon of f. And given their natural transformation, it means these two parallelograms commute. Probably you have seen this a lot, but it's a good thing to remind. And the extra condition is that we have the triangle diagrams to commute as well. So we have these two diagrams. I'm going to use this language like going down and up is the same as going from left to right. So if you want to have an interleaving distance, you want these 4 diagrams to commute. And I say epsilon interleaving, but actually it's like a T epsilon interleaving because we're using a notion that is called flow. So this was defined by Vinda Silva, Elizabeth Munch, and Anastasios Stefanou. And it's a way to be able to generalize interleaving to any category. So what they do is they take for each epsilon a monotone function inside the poset. So basically for each epsilon, you have a function that tells you how to jump into the poset. And you always jump forward, so you have these 2 extra conditions that tell you that. So this is a way to say how to chief by epsilon in any poset, not only in the line. Like in the line, you usually have the plus epsilon, but you can have other ways to jump. Oh, I think I forgot to put that, for example. I can go back for a second. Here, the way to jump in mapper graph is doing thickenings of sets. So you can be really imaginative in the way you jump into your poset. Okay, so you have your interleaving. And now your interleaving distance is taking the infimum of those epsilons such that the 2 elements are T epsilon interleaved. So that's going to correspond to the interleaving distance between the models. And this distance can be infinite if there's no T epsilon interleaving. So this actually is extended pseudometric, because you can have infinite. And that's the definition. But I know it's a lot of words. So what if we do an example? Examples makes our life easier. So consider, for example, a poset that is a natural set, not natural numbers, and the category is just sets. So for each natural number, we give a set. So when you have models on that category, F and G, they're called merge trees. So for example, for F, at 0, we assign this set, at 1, the other one, at 2, this set with 2 elements, and so on. So they look like trees, like they have branches and they merge, so they're merge trees. And the flow that we are assigning is for each epsilon, it takes m to m plus the floor of epsilon. So we're just doing the plus that I was saying before. So if we are at 1, we are doing T1 of 1, it's 2. So we're just adding 1 element to jump into the next one. Okay, so now we have 2 merge trees, we have 2 persistence models, and we like to know the interleaving distance. So maybe we can try to find an interleaving. And let me choose, I'm gonna move you here, perfect. 1 as the step that I want to use. So it means I'm gonna do an arrow by achieved by 1. So A0 and B0 are sent to C1, and A1 to B and B1 are sent to C2. And we have to send them because that we want that parallelogram to commute. So you can follow any of the elements in 0 and check that they go on the paths of the parallelogram to C2, which is nice. But if I try to do the next arrow, that will be like C going up from G to F. I need to assign C1, let's say, to A2. And now we have a problem. The triangle that we were talking before about it has to commute, it does not anymore with this particular attempt that I was doing to do an interleaving. So let's focus on B0, goes to C1 going down and goes to A2 going up, but from left to right goes to B2. So now that triangle does not commute because they're going to different elements, A2 and B2. So what is the problem? Maybe they're actually one interleave, but T1 interleave, but maybe we didn't have a good one, a good attempt, or maybe it's just F and G are not one interleave at all. So maybe we need to make bigger that gap, like that number that we are using to jump. But it's hard, it's NP hard, it can be NP hard sometimes. So what we're gonna do is try to do those attempts. Let me see what is my next one, yes. So we're gonna give a name to those attempts. We're gonna call them assignments. So for a fixed epsilon, a T epsilon assignment of F and G is a pair of collection of morphisms such that they do kind of the same thing as the natural transformation. They go from F to the shift by epsilon of G, and the same with C. But now we don't have any promise of commutativity. So now these are attempts of interleavings, but they are not. So what it means? It means that these diagrams do not necessarily commute. Like these parallelogram diagrams, you can still make them, but it doesn't mean when you take an element goes to the same element here at the final vertex. And far less these diagrams. If you don't have the parallelograms, maybe you cannot expect at all the triangle diagrams to commute. So now our idea is take this T epsilon assignment and try to make it an interleaving. But you can be unlucky and they are not. So now what we need to do is to find a way to measure that loss. How far are these assignments to be an interleaving? And this whole framework, again, was done in this research for interleaving between mapper graphs. So the way they decided to do the loss is by using a distance that we call the merging distance. It means how much we need to flow to attain equality. So what I mean, maybe I'm going to show the example. Perfect. Let's take G. And consider these two elements in G3. So B3 prime and C3. They are not the same, but if I take the image 1 and 2 steps ahead, I can see that both of them are mapped into C5. So I'm going to say the distance between B3 prime and C3 is the infimum, such that if I flow forward by that infimum delta, so if I flow forward by delta, they are the same. So this is exactly what is here. I use epsilon. So the minimum epsilon, such that if I flow forward between A and B, they are mapped to the same element. And we have 2 here, and we, for example, take C3 and C3 prime, we can see we just flow forward by 1, and they are the same as C4, so the distance is equal to 1. So now we have a way to measure if I have 2 different elements, maybe you can see where I'm going. If I have 2 different elements jumping, going at the end of the vertex, then I'm gonna measure how far they are to be the same. So let's do that. Okay, so imagine that I have an assignment, a T1 assignment. Phi and C. And let's focus on the parallelogram defined by 0 and 1. So we are focusing on this diagram. So I'm going to take an element of f of 0. And let me see if I can take my highlighter. And I'm going to see the image on the upper path. So this corresponds, let's see, to this bit here. So I'm taking one element, let's call A, inside f of 0. And I'm seeing the image exactly at D2, but on the upper path. But I can do the same, and I can do it on the lower path. Let's take green. And that's gonna give me a different element, not necessarily the same. But if they're different, I can take the distance. Now we can go back to the highlighter, the pointer, the distance, and I can take all those distance and take the sum over all the elements. And I'm gonna call that whole thing exactly the loss of this parallelogram diagram. So I'm defining, if I take all the elements, the sum of the distance between all the images that I have at the end of D2. So let's go with the example. It's gonna be easier when we see it. So it means we need to check all the elements inside f of 0. So A0 and B0. Let's go with A0. A0 goes to Z1, goes to Z2. Good. A0 goes to A1, goes to Z2 on the upper path. They're going to the same. So it means the distance in this particular case corresponds to C2 with C2, which is 0. So we don't have, we have a commutativity there with A0. But if we try with B0, B0 goes to Z1, goes to Z2 on the lower path, but now B0 goes to B1, goes to C2 prime on the upper path. Now the distance between these two is here. It's equal to 2. As we saw before, we need to flow 1 and 2 to have exactly the same element. And now it means the loss of this whole parallelogram diagram is equal to 2. So now we have final loss. That diagram has loss equal to 2. And we can do exactly the same with the other diagrams. So for example, we can do the same thing with the triangle. Maybe I'm not going to use the highlighter, just say like we can go from left to right, which corresponds to this portion, or down and up, this portion as well. So similar thing, I'm just going to check in the final vertex of the diagram if the two elements are the same or not. And if they're not, I'm just going to compute the distance. I'm going to plug in my computer. It says it's low battery. Got it. Perfect. So now we do the same thing really quickly. A0 goes to Z1, goes to A2, and A0 goes to A2 from left to right. We are good. It commutes. If we check B0, B0 goes to Z1, goes to A2, but B0 goes to B2 from left to right. They are not the same, but the distance between these two elements is equal to 1. So the loss overall of this triangle diagram is equal to 1. I think everything is all right. Maybe Bastian can say yes. Perfect.
Yes, sounds good.
Thank you, Bastian. That the feedback is important, right? So now we do the same thing for all the diagrams. So we fix a T epsilon assignment, and we do the same for all the 4 diagrams that I showed you at the beginning. And now we say the loss of the overall assignment is the supremum over all the loss, over all the diagrams. So the loss here on the bottom is defined as the sub over all the pairs of elements PQ inside the poset of the loss over all diagrams. So they can be a lot. Like if you have infinite elements, then it means you have infinite diagrams, but we can define it theoretically. It's okay. We don't have bounds in the theoretical land. So our first main theorem is we can bound interleaving distance by this loss. To be specific, you can take a T epsilon assignment, and then the interleaving distance between these two modules, it's going to be bounded by epsilon plus the loss. And the proof is, let's say, kind of simple. If you set the loss to be delta, you can just take your assignment and shift it by delta. So the big C and the big phi and big C. And there are going to be actually a T delta T epsilon interleaving of F and G. And by the properties of the flow, it means there are T delta plus epsilon interleave. Therefore, the interleaving distance is smaller than delta plus epsilon, which is exactly the result here. So that's really nice. And if we go to our example, we were taking a 1 assignment, and you can check when we were doing the loss that the maximum merging distance that we have was equal to 2. So the loss is bounded by 2. So 1 plus 2 equal to 3. So at the end, the interleaving distance of these 2 particular elements is equal to 3, or bounded by 3. And 2 things to say. The catch is this is not tight. Like we can be really unlucky and have a loss that is equal to infinity. The loss comes from the merging distance, and maybe not in this particular case, but imagine we have a second branch here. Maybe we have an assignment that sends 2 elements that are in branches that never merge, so the distance is equal to infinity. So we are not that lucky to have a tight bound, but the trick here is you can start with an assignment and start to make it better using the loss as your cost. And that's actually what another student of Liz is doing, Ishika. She's taking the mapper graph. She has the whole thing in a code already. And she has an assignment, she calculates the loss, and then she's able to improve that assignment using that loss. So that's the idea. Like we have these attempts and we want to make them better using that loss to have a better type to find the interleaving distance between 2 modules. So maybe I'm gonna say it again. It's gonna be my first takeaway. So we are giving random, or not random, but we are giving FG persistence models on concrete categories. So any poset, any category that is concrete. And we have been able to define a loss function that looks like this, such that the interleaving distance between them is bounded by epsilon plus the loss. So we did a really good job, but now we're going to the second part of the talk. And it's 11:20, perfect. Second part of the talk. So now we want to optimize this L epsilon. We saw that they depend of the elements in the poset. Now this should be a less or equal. And now we wanted to make a finite number of them. In particular, when the poset is a product of linear orders, complete linear orders. So that's the second step. We want to optimize this thing. So I'm going to try to show the idea. And the idea is to compute the loss between constant intervals. So I just want to be precise. By complete linear poset, we mean complete. It means that if you have a set and it's bounded below, then it has an infimum. If it's bounded above, it has a supremum. So the real numbers are complete. The rational numbers are not complete. We don't have those infimums and supremums. And linear just means, well, that you take 2 elements and they're comparable to each other. So you can put a poset like a line. So a complete linear poset. We say that I is a constant interval of a module if for all elements inside the interval, the morphism associated with the P smaller than Q is an isomorphism. And we say that t is a critical value of that module f if for any open on interval that has t on it is not constant on I. So probably you saw this already. You have, when you have aligned this nice decomposition on the intervals, and you know exactly like the endpoints of the intervals are critical points. So if I step up C1, the morphisms that go from before C1 to after C1, there are not isomorphism. And the intervals that are constant are exactly the intervals before. So maybe I'm gonna take a pen at this moment. So for example, the interval exactly between C1 and C2, where I'm saying Ci's are exactly the critical values of F, it's constant. So whatever is here in your category is the same. It's isomorphic. So the idea of the proof that we're gonna do is we wanna take intervals that are constant on a model F, for example, this second one, that when we map using T epsilon, using the flow, they are mapped to constant intervals. So maybe let's use another color. What about blue? Yeah, so this second one, interval is constant interval that it's mapped to a constant interval. And I'm gonna choose a representative of that interval, A12. So my idea is instead of taking the loss of all the diagrams of all the elements, what I want to do is take the loss over only on the specific numbers that I call in here on the bottom A. So I'm just taking the critical values and I'm taking this A's, A11, A12 that represent these intervals that are constant, that are mapped to constant intervals. Okay. So to do that, I need to give a definition. I'm gonna say that T epsilon assignment is constructible if for elements that are in a constant interval, then we have that the loss defined on the parallelogram of those elements is equal to 0. And similarly, if we take elements that are in constant intervals of G, we have the same thing. So what I mean is I want to take exactly, did I take the highlighter? No, I did not. There you go. For example, A11 and A12 are on the same constant interval, so I want this whole parallelogram, the loss to be 0, to always commute. So it makes sense that I'm gonna take only elements that are from different constant intervals, because the ones that are inside are commuting. So I'm gonna take those particular kind of assignments, such that the only thing that I need to care about are elements in different constant intervals. So that's the idea. The thing is, this is the line. It's kind of easy to do it. You have exactly that way to split it into constant intervals. But now we want to generalize it to any product, any t to the power of k. So what are we going to do next is that. So just recalling the idea, we want to find constant intervals, split them into constant intervals that map to constant intervals, so the blue one that I did here, and then choose a representative so that I can calculate or compute the loss over those representatives instead of the whole set. So we need to first define what is a constant interval. So we say that T is a critical J coordinate of these persistence modules that go from the power T to the K to C. If there's some collection of elements, K minus 1, such that if I put T as the J coordinate over all those elements, that whole element is a critical value of this persistence module that is just moving exactly at that J coordinate. Examples are better to see this, right? So it means, imagine that I have a model. In this particular case, let's say T squared goes to C. So we have critical coordinates, let's say X and Y, the horizontal and the vertical. So I'm going to say X4 is critical. And again, I'm going to change it to a pen. It means if I have a point here, exactly on that line defined by X4, such that if I go into this direction, that point is critical on that red line that I just drew. So I can have multiple, I can have infinite number of those critical numbers. The thing is, it's like that X4 is dividing my plane into some vector space, let's say, and is not isomorphic to the vector space that was on the right. So the left and the right, when you cross exactly that coordinate, are not isomorphic. And I'm just asking to have a finite number of those. So now we can split our plane, but then you can think again in k dimensions, our k-dimensional space into these cubes that I'm gonna call S. So let's go back to the highlighter. Nope, the laser point. So these A's, S, S, I, J are gonna be products of intervals that are either the critical coordinates or the open intervals between the critical coordinates. So what I mean, for example, S23 is X2 cross the open interval Y2, Y4. Or S33 is the product of the open interval X2, X4 with the open interval Y2, Y4. So now I can divide my whole space into these little cubes that I'm calling S and index corresponding to the critical coordinates. And the lemma is these cubes. Now, if we're going to K, I can index by the elements that I have as critical coordinates are constant intervals of F. So I can prove that these little portions are constant. Like if I take two elements inside, let's do again the pen. I can connect them. It's convex, and then it's gonna be an isomorphism. And I can prove that to you. Okay, so now we have doing it beautifully, divide our plane into constant intervals. The first step is done. Let's go to the second step. The second step is we wanted to divide this constant interval into things that map to constant intervals. So we have those Sij's that are constant intervals of F, and we're gonna call the RKLs, and this is the point, my tongue is gonna twist, that's the word, are gonna be the constant intervals of G. So here I kind of put overlap one over the other. So the idea is for each of those Sij's, I wanna consider those RKLs such that the image of the Sij's are mapped into those RKLs. And I'm taking the infimum on that of those specific points. So I'm taking the infimum of all the elements into Sij that are mapped into RKL. So we can see the example here, this whole region, I'm gonna call it I3333. Because, I1333, sorry, because the elements of S33 are mapped into R13. So I know it's a lot of indices, but you get the idea. So maybe I want to be even more explicit. So you can see this region is exactly on S33, but it's mapped on R1. And I'm going to do that for all the elements. And I'm defining these A's, and these A's are going to be the ones that define this region. So this particular interval is between the X coordinates of these A elements into the Y coordinates between the A and the Y4 in this particular case. So these A's are going to be enough in order to split this S into these constant intervals. All right, everything good? Perfect. So now the third part, we want to choose representative for each of these little pieces. Okay. Now we need to do a step that in the line we didn't need to do before. So imagine that we are here on the top, on the S34 line. If I take any element inside the line, let's say that's a circle, all the elements inside that interval are comparable. And if I take anyone here, it's smaller or above. So taking one in the middle or whatever, it's enough to compare them. But I cannot do that with the square. Let's consider this P. Maybe I want to change the color of my pen. Let's do to red again. All these elements are above P. And all these elements on this lower quadrant are below P, like using the order that we have when we have a product order. But then these, I'm going to put it in green, these quadrants are not comparable to P. Like I cannot say they're greater or smaller than P. So it means it's not enough to take one point in the middle. I need to take the smallest one, will be exactly the corner. It's only the corner, the one that is comparable to everyone, that is smaller than everyone. But now if I take the corner, in this particular case will be this A3313, the corner belongs to the line. But then if it belongs to the line, I cannot guarantee it has the same, is not isomorphic to the interval that was coming from. So the whole idea was taking a representative of the interval. I'm taking an element that has not the same image. We have a problem there. I'm gonna erase this because this has a lot of things. So now we need to create a new element, a new poset that is not even related in the terms of it's exactly into T squared, but we need to create a new poset of representatives that has that property that it's smaller than everyone in some sense, but now it's isomorphic or it belongs to the interval. So that's the reason I'm gonna do this construction that we have on the left. We're gonna define this poset P hat. Dun, dun, dun. As all these elements, I'm gonna call A hat, KLAJ. So each of these A is associated with this infimous that we talked before. But now we're putting this S extra that corresponds to compositions of the epsilon. It's gonna be clear in a second why I'm using this in this way. And now I'm gonna use the inverse limit to define a new functor that goes to this new P hat, F hat. So for each of them, I take in the inverse limit of the images of all F of SP, where P belongs to the interval. Yeah. Let's delete here. So now let's go back again to the example. It means, let's do orange. Oh, it's green already. Okay, so remember that green that we used before here? So now this whole interval S34, it's gonna be represented by only this point, A3413. All the elements that are in 34 that are mapped into 13, into R13. We can do the same with the squares. So the whole square is constant and is mapped into constant things. It's gonna be represented only by this point, this new A hat. And even the points themselves, oops, I did an extra one, it's fine. This little point itself is represented. All the constant intervals that are mapped to constant intervals are gonna be represented into our new poset P. I revealed the lemma, but it's gone. Okay. So now this is a whole construction that is behind that I'm not showing. We need to use the universal property multiple times in order to define all these things that I'm showing. So we can do a new G hat. We need to do the exact same thing, G hat, and put it G here. We can define this phi and C's maps, but then we need it to be constructible. We have a whole thing behind when we are doing this construction. The point is, at the end, this kind of parallelograms and triangles exist, and even we can define the loss of these diagrams. So the S that I put here at the beginning is just, I want to take in account all the possibles, T epsilon, T delta, T epsilon, and all the construction that I need to do in order to even define a loss in the diagrams. So it's a whole poset, like there's more things than here. And now the lemma is, if I take phi and C to be a constructible assignment between F and G, and I take two elements P and Q that are here on the top, that are on the same Sij, but are mapped into different RKL. So this P is mapped into RKL, and this Q is mapped into the KL prime, K prime, L prime. The loss between these two elements in the parallelogram diagram is bounded by its representative, the loss of the representatives, and similar here with the triangle. So if you forget the construction is fine. The whole point is, if we take two different elements, again, let me take my pen, P and Q, the parallelogram defined by these two elements, it's bounded by the parallelogram defined by these two representatives. So at the end, I'm able to take this whole plane and summarize it into a finite number of representatives that are gonna bound the loss. So now I only need to calculate the loss over those representatives, because it's gonna take, when we're taking the supremum, it's gonna be enough to find the loss overall. So that's the whole main term. The second main term is, if we have a poset T, again, a complete linear order, and two different models that go from Tk to Z, to T to the power of K to Z. And there are 10, we have a finite number of critical coordinates. If we have that assignment to be constructible, we have this whole thing that is the loss. But the point is, we are taking the loss of the triangles over a finite set that is called P hat, and over a finite set of elements that is called B hat, where B hat is just some kind of minimality into those elements. So for example, between A3413 and A3423, I'm taking just the first one, but it's just a technicality. The point is we are able to reduce, it can be infinite if we are near real numbers, to a finite number of them. Cool, yeah, so we go to the whole plane, 2 representatives. 5 minutes is the time that I need. So just to recall, my second takeaway is we take a lot of elements, and now we're able to reduce the formula to checking only loss into finite number of those. Perfect. We are in the right track. We have checked the first one. We have checked the second one. And the third one is, if you see here, those little each portion can be not polynomial. So the thing is, we're going to show we can compute these portions Li that I called before in polynomial time when we have categories that are either with finite objects or objects with underlying finite sets or of vector spaces. So perfect timing. Perfect. So recall that the calculation of the loss involves the merging distance function. So for example, if we take the triangle, the finite one, so maybe we start here, maybe we're going down somewhere and coming back. The loss was defined by the distance between the elements. So if we go back to our example, we saw that B3 prime and C3, the distance is equal to 2. Or C3, oh, we did B3 prime and C3. Did I did something wrong here? Yeah. Okay, this should be C3 and C3 prime. But anyhow, it's equal to 1. The point is, it's exactly 1 and 2. We don't expect it to have 0.5 or 0.7, because it's exactly at 4 and at 5 that we have a reduction into our merge tree, right? It's exactly at 4 that we came from 3 to 2 elements and from 2 to 1. So at the end, when you're calculating the merging distance, you don't need to check in each flow, you just only need to check exactly at those points that are not injective, are not monomorphic. So let's give a name to those. For a fixed Q in P, in this particular case, let's say 3, in the natural numbers, delta is a reducing constant of Q on G if for all elements that are below and above delta, so gamma 1 and gamma 2. The morphism defined there is non-monomorphism. So what it means is exactly in between moving by 1, so flow by 1 exactly here is non-monomorphic. So I just want to say it again if it was not clear enough. So if we want to check the distance between elements in 3, we only need to check by 1 and by 2, because those are exactly the moments that the function stops to being injected. That's exactly when we have a merge, and we can expect to have an equality of those when we map them. So the last theorem is, if we fix P and Q, and we fix this parallelogram diagram that we have on the top, and we assume that here at the end, we have just a finite number of moments that we need to check that merge. So for example, this corresponds to GT epsilon Q. Yeah, I can go here for a moment. If I take one element A of f of P, if I'm doing my loss on the parallelogram diagram, it means I need to check the image of alpha, the upper path, and the image of beta, so beta A. So I need to check how far they are, right? And we need to do it only finally many times, corresponding exactly on those reducing constants that I'm calling them in a finite set D. If that's the case, when we have finite underlying sets, the computation is the order of the number of elements I need to check, so the numbers of A that I'm starting with, multiplied by the log of D plus 2, where D is the number of times or the number of positions I need to check. And this log comes from a binary search over those. And we can do a similar thing. If we have the vector space over some field M, and we have Q10 models, which this Q has nothing to do with the Q on the POSIT. It means the rank is finite when we have those maps. The time required is the rank of alpha minus beta. Let's say it's the same. So we just consider ranks of the maps times the log of how many times we need to check. So again, the takeaway is we can compute this loss on each of the diagrams in polynomial time. So third and last takeaway, this is my summary. So if we have two different persistence models, any POSIT, any concrete category, we have the final loss function that takes a sum over an infinite number of elements. such that the interleaving distance is bound by epsilon plus the loss. But in the case that we have, for example, deposit R2, R3, any linear order to the power of k, and see, let's say, the vector spaces, we have a formula for L epsilon that requires to calculate the loss for a finite number. So we have reduced these pairs to a finite number, and each Li in polynomial time. So this whole thing is to say affirmatively that we can bound interleaving distance between n parameter persistence modules in polynomial time. Like if you put those together, we can calculate this bound in polynomial time. And yeah, I think that's all, 11:41. So I think that's a good timing, and thank you so much.
Thank you so much. Let's all briefly unmute and give a round of applause for Astrid. Right. So, do we have any questions from the audience? I don't think we have anything in the chat at the moment. So, maybe let me start with one, namely, this is really cool that this that we now have this polynomial time proof. What I'm always thinking about when I hear these things is, would it also be possible to optimize this loss function now based on like some kind of like optimization scheme? Because that's where I thrive, right? With all these machine learning machinery. So is that a, do you think that this is a possibility to like make that actually like learnable?
I see. I don't know. That will be the next frontier. Maybe with vector spaces, we have a nice way to be able to calculate the rank at the end. One thing that we have here, maybe I want to go back here. Yeah. Like even though we are passing to this inverse limit thing, at the end you only need to take an element that has the same, is isomorphic to anything that is in the interval. So probably it's not that hard to be able to pass into these representatives without actually doing an inverse limit or something, just taking one element that looks exactly the same. So I'm guessing maybe it's possible, but I'm not sure how to do it.
Yeah.
How to go into the Ishika's code and try to put it into this.
Yeah, neither am I. It's mostly like I think you opened the door to that, or Pandora's box, if you will, to these type of things.
Yeah.
Yeah.
That's a good question. That's what Liz wants to do. She's like, oh, now in a computer. I know it's hard, but it's a good thing that we can do. So maybe.
Exactly. Maybe as the next step, right? Do we have some other questions from the audience? Please either unmute yourselves or raise your hand or type a question in the chat if you don't want to speak. So again, then let me maybe circle back to like a minor technicality, but just in case I got that, I might have missed that, or I want to make sure that I understand this correctly. So there's, what you proved is that you don't have any restrictions on things like coefficients or like the type of underlying module structure that you use, right? So this is like super general, right? This is the general setting. I got that right.
Yeah, like the merging distance only needs to be able to compute between elements. So there's no restriction before doing the construction. Is after in the optimization that you need some control into the elements that you have.
Okay, very nice. Okay, no, then I'm glad that I got this. But this it's really a nice result. I like that.
Thank you.
So maybe let's look at the audience for some more questions. Anyone else wants to ask something? I feel a little bit bad hogging the question space. Otherwise, let me maybe circle back to a simple one, and then maybe maybe we see where that takes us. So I mean, this is now for the interleaving distance. Do you I really don't know any I really don't know the answer. I really don't know where this is going. But do you think that there are some relaxations of the interleaving distance that could be that could be used as well.
What do you mean?
Since I mean, yeah, often when we do just like normal persistent homology or whatever, right? Then we do bottleneck distance or Wasserstein or something like this, and then we even have ways to approximate those nowadays. Although like the approximations are, some of them are good, some of them are less good, right? So I'm just kind of wondering, do you think there's space for like an additional distance that is maybe sandwich between between a couple of these distance measures that already exist in terms of like computability and expressivity? Sorry, that's long question, but I generally am interested in what someone who works on this for a living, what they think.
Yeah, I'm gonna say I don't know. I think the idea here was be able to generalize this idea that went from upper graphs. I don't know how the space of those distances that you're talking. So I will need to go deeper into that in order to answer that question, because I don't know.
Okay, yeah, no, I mean, I also don't know. I was just kind of wondering because it's always interesting to see. I think when the interleaving distance first came out, and there was like this very cool result to show that we have the bottleneck distance as well, right? These sort of things that's really neat. And now I'm just kind of wondering whether something else would also work. But yeah, no, I guess we'll see.
Okay, for sure.
So yeah, so any other questions from the audience? If not, let me thank you again, and I'm just going to stop the recording. So thank you very much for being with us today.
Thank you so much.